Good afternoon, dear students. Again, I welcome you all for the subject of refrigeration and air conditioning. And today we will discuss the last part of your unit number 6, which is related to the numericals or problems of psychrometry and the load estimation. Basically, this last part of numerical we will have in 2 or 3 parts. This is the part number 1, where we will solve some basic problems of psychrometry and the load estimation. And related to the cooling load estimation, heating load estimation, their designing, that we will cover in the part 2 and part 3. So let us begin with part number 1. We'll have problem number 1 here. So here you are having problem number 1. Along with that, we are having its given data also. You can read it. Okay. The following data refers to the air conditioning of a conference hall. The outdoor condition are 40 degrees Celsius DBT and 20 degrees Celsius WBT. This is the outdoor conditions, means atmospheric air conditioning. Required comfort conditions are 20 degrees Celsius DBT and 50% RH. This is the comfort conditions. Now, as it is mentioned in the first line, it is for the conference hall. So the sitting capacity of the hall is 1000 occupancy is there, and the amount of outdoor air supplied is 0.3 meter cube per minute per person. Okay, so whatever the air you are supplying, the conditioned air you are supplying for per one person for 1 minute, it is 0.3 meter cube. This much is the volume of air you are supplying for one person for 1 minute. Now this required condition is achieved first by adiabatic humidifying and then by cooling. Okay, you can see the outdoor and indoor condition. Okay, outdoor and comfort condition, that 40 degrees Celsius is outdoor condition and 20 is indoor condition. Okay, so obviously you are going for cooling, and at the same time it is mentioned that you will have to achieve the humidification also. So it is required that first you will go for adiabatic humidifying and then you must go for the cooling. One after one you will have to achieve the stages. What you have to find out: the capacity of cooling coil and surface temperature of the coil, that is also called as ADP. Okay, appress dew point temperature, that is effective temperature of your coil. That could be cooling or heating coil. In this problem we will have to deal with the cooling coil if the bypass factor is given as 0.25. Okay, and at the same time, second thing what you have to calculate, that is capacity of humidifier and its efficiency. Okay, now we have sorted the data. TD1, that is 40 degrees Celsius, with TW1 20 degrees Celsius. This is outdoor condition. Dry bulb temperature and wet bulb temperature is given. For indoor condition, dry bulb temperature is given as 20 degrees Celsius, whereas the relative humidity phi, that is mentioned as 50%. Volume, that is 0.3 meter cube per minute per person. So for total hall, the total amount of air what you are supplying, that is 300 meter cube per minute. Okay, we just have multiplied that with 1000 because the sitting capacity is of 1000 people, and the bypass factor, that is 0.25. Now whenever you will sort it out the data in any problem of psychrometry or cooling load estimation or simply unload estimation, first of all locate these points, locate these conditions on psychrometry chart. Okay, now let us locate it. Point number 1, that would be of outdoor condition, 40 degrees Celsius DBT and 20 degrees Celsius WBT. And point number 2, it will be for 20 degrees Celsius DBT and 50% RH. Okay, now this is your psychrometric chart. Already in unit number 4 we have introduced this particular chart and various properties associated with psychrometric chart, various terms you can find it out. Okay, now first point we will have to locate with 40 degrees Celsius DBT and 20 degrees Celsius WBT. Now this is that point. You can see here this is 40 degrees Celsius DBT, and here we are having around 20 degrees Celsius WBT. This particular line, the intersection of this line, we are getting at point number 1. Fine. After that, we'll have to locate point number 2. Point number 2, again it is 20 degrees Celsius dBT and 50% RH. Now for RH, we are having this curve, 50% RH, and this is 20 degrees Celsius dry bulb temperature. Now both the points we have located. These 2 points we will have to join like this. This is indoor condition and this is outdoor condition, that is point 2 and point 1. We'll have to move from 1 and we'll have to reach at point number 1. But in the problem itself, it is mentioned that the required comfort conditions are achieved by adiabatic humidifying and then by cooling. Okay, so first we'll go for humidification. We'll add the humidity in that particular air in order to condition it, and after that we'll go for the cooling. Now, as we'll have to go for humidification, we'll have to increase the moisture in that particular air. So at first, let us represent the humidity at point number 1 and point number 2 like this. The green lines what you are observing, you can get W1, that is around 0.06, 0.06 something, and W2, that is 0.07 something, you'll get it. Okay, this is point number 1 and point number 2. From point number 1, if I want to reach the point number 2, I'll have to follow the path that first I'll go for humidification. Okay, first I'm going to add the heat, and after that I'll go for the cooling process. Now when I'm going to add the heat, I'm going to add the moisture, the path would become like this. Okay, because we don't need to change that particular temperature or that particular cooling procedure, we'll just have to increase its humidity. Okay, so there I can locate point number 3. Okay, 1 2 3. Okay, we have just added the water vapor in that particular air. Okay, now from point number 2, from point number 3, we'll go for the process of cooling. Now this is the cooling process, 2 to 3, 3 to 2, and by means of this you have added the humidity as well as you have reduced the temperature. 1 to 2 is total process, and 1 to 3 is adiabatic humidifying, and 3 to 2, that is the process of cooling. Now from this you will have to take it out certain values of enthalpy and specific humidity. Okay, on y-axis, on this particular axis, if you are observing, you are getting the humidity, and on this particular lines you will get the values of enthalpy. So just take it out all the values, and at the same time take the values of this. What is this? This is your specific volume. Note down the specific volume at point number 1 and point number 2. All the values you will have to take it out from this psychrometric chart after plotting their correct positions. Okay, now from psychrometric chart we got this value, VS1 specific volume at point number 1, that is 0.896 meter cube per kg of dry air. Someone, when you will solve the problem, everyone will get certain different values, plus minus of 10%, let me say. Somebody would get 0.85, somebody would get 0.9, so all are correct values, but you will have to take it proportionately. Now we'll have to calculate the mass of air supplied. When you are going to calculate the mass, you required the total volume and the specific volume. So we have all these two values. Total volume, that is 300 meter cube per minute, and specific volume, that is 0.896. Now the first thing what you have to calculate, that is cooling capacity. Okay, the cooling coil, whatever you are having, its capacity you will have to calculate, and at the same time you will have to calculate the surface temperature of the coil, that is ADP. Again we will use the properties which we have taken from the psychrometric chart, because cooling, it is only process 3 to 2, right? because 1 to 2 was your humidifying, adiabatic humidifying, and 3 to 2 that was your cooling. So when I'm dealing with the capacity of cooling coil, I'll just have to focus the process 3 to 2. So at point number 3, enthalpy is 57.6, and at point number 2 it is 39.1, and at the same time I got the temperature at point number 3, that is dry bulb temperature 38 degrees Celsius. Now capacity, when I'm calculating, it is simple formula, how much heat is get removed in that particular process. So the mass of air multiplied by the enthalpy difference, that is H3 minus H2, and we'll get this 6227 kilojoule per minute divided by 210. You will get it in TR, that is tonnage of refrigeration. This is the first thing you have calculated, that is cooling capacity. Now when you have to calculate the surface temperature of the coil, or what you can say, apparatus dew point temperature, you need to use the term bypass factor. Now what is a bypass factor? Now this is just for general information, you don't need to do it in the solution. See, this is the passage. Okay, this one is a passage through which the air is flowing. Okay, this is your outdoor air and this is your indoor air, the air which is required in the room. So outdoor air, it is having temperature TD1, okay, and its mass is, let me say, 1 kg. Now this 1 kg of mass which is flowing through that particular passage, okay, it is coming in contact with this coil. Now that could be heating coil or that could be a cooling coil. As I've said that the 1 kg is total mass, it is flowing through that particular passage, but out of that, let me say x kg is a mass which is untouched to that particular cooling coil, which is not affected with that cooling coil, x kg. So 1 minus x is a total mass which comes in contact with that particular cooling coil, which is affected by that cooling coil or heating coil, whose temperature is TD3. Okay, and after passing through that coil, when it comes out from that passage, its temperature is TD2, which is your required value. Okay, now TD1 is entering temperature, TD2 is exit temperature, and TD3, that is apparatus dew point temperature or that coil temperature, simple one. Now if you'll take heating coil, obviously the temperature of this TD3 would be high. Okay, that would be used in the winters. Okay, so the this outdoor temperature, let me say it is 20 degrees Celsius. This particular temperature, let me say it is 40 degrees Celsius, and this would be around, let me say, 35 degrees Celsius. So accordingly you can easily calculate the bypass factor. Okay, at the same time you may go for the cooling coil also, that would be used in the summer air conditioning. Correct, air in, that would be at the higher temperature, and the cooling coil temperature, that is effective surface temperature of coil, that would be less. So again you will have to calculate the bypass factor. Now this bypass factor, this particular formula, you got it from the energy balance equation, taking the enthalpies at 1, 3 and 0.2. After that you got this particular formula. You can see for heating it is TD3 minus TD2, okay, coil temperature minus exit temperature divided by coil temperature minus entering temperature. That ratio has to be low, as low as possible. Again, when you are calculating for cooling coil, it is TD2 minus TD3, because this temperature would be the lowest temperature when I'm talking about the cooling coil. Okay, it would be 5 degree, 10 degree, 15 degrees Celsius at the max. This would be the highest temperature, that would be in between these two. Okay, so TD2 minus TD3 divided by TD1 minus TD3. This way you will have to calculate the bypass factor. Just only 3 temperatures you will have to take: inlet, outlet and coil temperature. Now this formula we will use when you are going to calculate the surface temperature of coil. Now we have bypass factor given as 0.25. We have this formula. Now TD4, what you have taken here, that is the apparatus dew point temperature. Okay, you can take any particular representation factor there, any indication, any notation you can use there. TD2 and TD3. TD2, that is exit temperature, and TD3, that is entering temperature for that particular cooling coil, and TD4, that is the lowest temperature, that is the temperature of your coil. We have 0.25 as a bypass factor, TD2, that is indoor condition, exit temperature of that air when it comes out from that cooling coil, and TD3, this is 38 degrees Celsius, not 40. 40 it was before humidifying, but after humidifying you got point number 3 where temperature is 38 degrees Celsius. Accordingly, you can calculate the surface temperature of coil as 14 degrees Celsius. Means coil temperature was 14 degrees Celsius. Over that coil there is a flow of air whose temperature is 38 degrees Celsius, and after that, when the air coming out from that coil, it is at 20 degrees Celsius, which is required condition. Now this is the second thing we have calculated. After this, the next part what you have to deal, that is of capacity of humidifier and its efficiency. Okay, now in this case you will have to take specific humidity in consideration. Again, by using psychrometric chart, after getting those particular processes, those points, we got this particular values at point number 1, because now we'll have to focus on process 1 to 3, because we'll have to deal with humidification. 2 point we will not consider at all, because that is after cooling you have achieved. We just have to take 1 to 3. So point number 1, we had W1 0.0064, and at point number 3 we had W3 0.0074, and dry bulb temperature is 20 degrees Celsius. If ideally you could have achieved the humidification process, okay, when the air is saturated. So capacity of humidifier, again, just like capacity of cooling coil, you can calculate the capacity of humidifier like this: total mass multiplied by W3 minus W1 after humidification. And when you will calculate efficiency, so this is actual drop in dBT, okay, divided by ideal drop in dBT. Ideal drop, that must reach to the saturation conditions, and at saturation we got dry bulb temperature, that is 20 degrees Celsius. So 40 minus 38, this is actual drop, and ideal drop, that would is 40 minus 20. So 10% is nothing but efficiency of your humidifier. Now this way you will have to solve the numericals on psychrometric chart. Hope you have understand this. Now we will move towards problem number 2. Now in problem number 2, it is said that 800 meter cube per minute of recirculated air at 22 degrees Celsius dBT and 10 degrees Celsius dPT is to be mixed with 300 meter cube per minute of fresh air, which is at 30 degrees Celsius dBT and 50% RH. Okay, now two airs and their motion has been given. One is a fresh air and another one is a recirculated air. Always the primary air which is required for air conditioning is nothing but your fresh air. Okay, this is point 1, you can say that, and point number 2, that is your recirculated, and they will mix together in a mixing chamber before they comes in contact with the cooling coil or air conditioning coil. Okay, so both the air and their properties are mentioned. Recirculated air, that is 22 dBT, 10 dPT and 800 meter cube per minute of volume, whereas the fresh air which you are taking from atmosphere, its temperature is 30 degrees Celsius and relative humidity 50% RH, and having the volume 300 meter cube. Determine the enthalpy, specific volume, humidity ratio and dew point temperature of the mixture. Okay, their mixture, we will have to take it and we'll have to find out these values. Okay, recirculated air, volume is 800 meter cube, TD2 22 degrees Celsius, TDP2 10 degrees Celsius, and for fresh air V1, TD1 and 5, that is 50% RH. Now we will again locate the values. We'll plot the process on psychrometric chart. Point number 1 and this is point number 2. Now this is your process. 1 to 2 is the process of mixing. 1 to 2, in between them somewhere you will get the mixing. Both the air are coming in a mixing chamber from 2 and from 1, and they will mix together at certain point in between 1 and 2. For that, again at point number 1 and 2 we got different values, H1, H2, W1, W2, that is specific humidity, and VS1 and VS2, that is specific volume. As we have the total volume of air, we have specific volume of air, we can easily calculate the mass of air. Again, mass of air supplied at point number 1, M1 is equal to V1 upon VS1. Mass of recirculated air at point number 2, M2 is equal to V2 upon VS2. And this is the formula you will have to use. Always remember, whenever there is a problem or there is any condition which represent the mixing of two air streams, you will have to use this formula. M1 upon M2 is equal to H3 minus H2 upon H1 minus H3, whereas the H3 is point number 3, where enthalpy is in between 1 and 2. Enthalpy of a mixture, that is point number 3, H3. Simply you will have to substitute the values, and after substitution you will get H3 is equal to 47.86. Now this point number 3, 47 point something, whatever the enthalpy you got, you will have to mark it somewhere here. Now at point number 1 your enthalpy is around, I think it's around 65-70, and at point number 2 it is around 40. So point number 3, which is the mixture, just now you have calculated, it is around 47. So 47, it comes here somewhere. So you can mark point number 3 here. And at point number 3, you will have to note it down the different properties of that mixture, just like specific volume, humidity, okay, and dry bulb temperature, wet bulb temperature, and some other values, specific volume also. Okay, now we have plotted the point number 3 on psychrometric chart, and at point number 3 we got this value, specific volume 0.855 meter cube per kg, W3, that is specific humidity 0.092, and dew point temperature of mixture, that is 14 degrees Celsius. Now we'll take problem number 3. 300 meter cube per minute of moist air enters a cooling coil at 35 degrees Celsius dBT and 50% RH. Okay, volume of air is given 300 meter cube per minute. Temperature is 35 degrees Celsius and humidity is 50%. They enters on your cooling coil. The apparatus dew point temperature, that is effective surface temperature of a coil, that is 5 degrees Celsius, and the bypass factor is 0.15. What you have to calculate? Condition of outlet air and the cooling capacity in tonnage of refrigeration. Now let us take out the given data. V1 300 meter cube per minute, TD1 35 degrees Celsius, 50% RH, ADP 5 degrees Celsius, and bypass factor. Now bypass factor is given, means you can easily calculate the temperature at second condition. At inlet condition it is 35. At outlet condition it can be find it out by using bypass factor. Okay, as it is a cooling coil, again bypass factor is equal to TD2 minus TD3. TD2 is exit temperature, TD3 is apparatus dew point temperature, divided by TD1 inlet temperature, and TD3 again it is apparatus dew point temperature. You just substitute the values and you will get TD3 as 9.5. Now you can mark these points. You can represent 35 degrees Celsius DBT 50% RH as point number 1. Point number 3 you can mark it as 5 degrees Celsius ADP, dew point temperature of 5 degrees Celsius, and in between them you can locate point number 2, that is 9.5 degrees Celsius, that is indoor condition, the air which need to supply to the room, that is at 9.5 degrees Celsius. Means you can simply say that air will come at 35 degrees Celsius and it will be conditioned and reaches to 9.5 degrees Celsius, and coil temperature was 5. Here I can locate point number 1. Point number 1 we have located with 35 degrees Celsius DBT and 50% RH. Okay, 35 degrees Celsius DBT and this RH. Fine. After this we have dew point temperature. Dew point temperature is how much it was? 5 degrees Celsius. Now this 5 degrees Celsius I have marked it here. This one, this 5 degrees Celsius, this line. Okay, so in between them you can join it like this, but it is not the process, because process would be completed when you will locate point number 2. Point number 2, by using bypass factor you calculated 9.5. So on this line you have represented point number 2 when the temperature is 9.5. Now again you got 1, 2 and 3. 1 to 2 is your air conditioning process, and point 3 it represents the temperature of your cooling coil. Again noted down the values of enthalpy, specific volume and specific humidity. Two things you have to calculate. One is a condition of outlet air, and second one cooling capacity of a coil. Condition, that is nothing but the properties at point number 2. Already temperature you got, that is 9.5, but along with that weight bulb temperature is 13.5 and relative humidity is 95% RH. Phi is equal to 95%. After this we'll go for cooling capacity of a coil. Mass flow rate you can easily calculate. V1 300 meter cube per minute. I have divided by 60 to get it in meter cube per second, and VS1 that is 0.895. So mass flow rate, or the amount of mass of air is flowing, that is 5.586 kg per second. Cooling capacity, as we have calculated before also, that is mass flow rate multiplied by enthalpy difference. So enthalpy at point number 1 and enthalpy at point number 2, we got it the cooling capacity as 262 kilowatt or 83 TR. Divide that by 3.516. Now last problem number 4. Atmospheric air at 35 degrees Celsius and 75% RH enters a cooling coil at the rate of 200 meter cube per minute. The coil DPT is 14 degrees Celsius. Okay, bypass factor is 0.10. Okay, the coil temperature is 14 degrees Celsius and bypass factor is 0.1. Atmospheric air which we are going to supply in that air conditioning coil, that is 35 degrees Celsius DBT and 75% RH, and the volume is 200 meter cube per minute. Again 4 things you have to calculate. Temperature of air leaving the coil. Okay, the air which is entering the coil is 35 degrees Celsius. The temperature of coil, that is 14 degrees Celsius. What do you have to find out? Temperature of air leaving the coil. Obviously that would be greater than 14 and lesser than 35. Then cooling capacity, again mass multiplied by enthalpy difference, then amount of water vapor removed in kg per minute, and last one is a sensible heat factor. Now this is your given data. Volume of air 200 meter cube per minute, TD1 35 degrees Celsius, phi relative humidity 75%, coil dew point temperature or ADP temperature, that is 14 degrees Celsius, and bypass factor is 0.15. Again, bypass factor is given, cooling coil is available. You can calculate the temperature of air leaving the coil. Again, simple formula you will use. Bypass factor is equal to TD2 minus TD3, outlet temperature minus dew point temperature or coil temperature, divided by inlet temperature minus coil temperature. We have everything except TD2. So it is 15.6. Okay, again it is greater than 14 and lesser than 35. Now we'll mark those points here. 35 degrees Celsius, DBT 75% RH, coil temperature is 14 and air condition is at 15.6. So this is point number 1. This is point number 2, that is coil temperature. After joining this, in between them you will have to locate 15.6, which is somewhere here, and this could be the available path which we can follow. Now this point A, I have represented it in order to calculate the sensible heat factor. Okay, this will not play any role when you will calculate the cooling capacity. Okay, cooling capacity, when you will calculate directly, you will take the enthalpy at point 1 and enthalpy at point number 2. Again, when you will calculate the amount of vapor, water vapor, then again you will have to consider point number 1 and point number A, because at point number 2 and point number A your specific humidity is constant. Only 1 to A it is changed. So point number A, it will be utilized when you will calculate the humidity, change in humidity and sensible heat factor. We have located all the points. 1, outdoor condition, 3, coil temperature, and 2, that is indoor air temperature. Now again noted down all the values, enthalpy, specific volume and specific humidity at every point. See, I got everything: H1, H2, HA, W1, W2 and VS1 also. So by using VS1 and the total volume given in the problem, I can get mass M1, that is 226.2 kg per minute. This is everything what we are doing. It is only for calculating the capacity of cooling coil. Now I got mass, I have H1, I have H2. I can calculate the cooling capacity as 8709 kilojoule per minute, that is 41.5 TR, or in terms of watt, that is 145.15. In first case you will have to divide by 210 and second case you will have to divide by 60. Now after cooling capacity we'll have to go for the humidity, that is amount of water vapor removed per minute. So point number 1 and point number 2, or you can say A. Okay, because at point number 2 and as well as point number A, humidity is constant. Specific humidity is 0.011. So amount of water vapor removed, that is M1 into W1 minus W2. W2 or WA, that is one and the same thing. That is 226 multiplied by 0.02 minus 0.011 and you will get it as 2.08. In 1 minute 2.08 kg of water vapor is removed. And last one, sensible heat factor, that is the ratio of sensible heat upon latent heat. Here I will going to use the point A and enthalpy at point A. I have enthalpy H1, H2 and HA. This I am going to use when I am going to calculate the sensible heat factor. That is HA minus H2 divided by H1 minus H2. H1 minus H2 is total heat. After accompanying the removal of water vapor and cooling, we got change in the heat, that is H1 minus H2, that is total heat. Whereas HA minus H2, this is the sensible heat. Because at point number 1, sorry, at point number A and at point number 2, at both the points, you can see that the humidity is constant. There is no change in the humidity. That is sensible heat. We know that sensible heat means there is no any phase change. Phase change means there is a latent heat. When you have to calculate the sensible heat factor, you will have to take a ratio of sensible heat and the total heat. Now total heat means sensible heat plus latent heat. Okay, 1 to A and A to 2, that complete together 1 to 2. So just substitute the values, you will get 0.377 as a sensible factor. So this 4 problem we have completed today. Another numericals which are remaining, that we will take it in the part number 2 and part number 3 if required. Okay, definitely part number 2 you will get it today or maybe on tomorrow, where we will solve certain complex problem related to the load estimation. Okay, where you will have to design the air conditioning system, where you will have to design the number of components of air conditioning system. So that we will cover in the second part. Okay, thank you.